Hi, good morning. Ashutosh. Maurya. Oh, what happened to that thing? Oh, when I missed that, the Zoom window, then it disappears. I didn't, not this one. Yeah. But I think what I'll have to do is, if I have to get the thing, I have to share it here. No, I think it'll be okay. Okay, this is okay for you, right? Huh? Is it, I can't be moving around, okay, because the thing. Okay, so hello. So I'm very happy to meet you after all these years. So let me try. Okay, so, or maybe you can introduce once more.
I am Soham.
Soham Pine. Okay. Yeah. I know your background. Okay. Rohan Dharmadipari, Nabin Sahu, Trivjyoti. Yeah. Ashutosh Maurya. So there are two other people in the class. The reason I Hardik Kalra Shauryam. Okay, the reason I'm saying is very soon we'll have to do some team mating. Okay, team making. Okay, so that so we will start working on the thing. So that's why it's important that you kind of. Get to know other your classmates. Okay, so first a couple of announcements. So tomorrow Diganta will have a tutorial. Okay, so that will be on this Marabou system. Okay, which has this reluplex. Okay, and since you'll be using reluplex as is deep poly and linsim, all three of the tools in your project. So that is the triumvirate of three things. And a couple of questions on the second part of your assignment 2 will have you use reluplex also. So he's going to give you instructions as to how to install Marabou, of which reluplex is a part. So try and attend that. Yeah. So today, what I want to do is, you already you see this. I've shown you this slide, several times. Let's keep it interactive. You can interrupt me. So and also today I'll have to leave by. I have to catch the shuttle at 6 o'clock. So 5:55, I have to leave here. So I'll keep it a short class. And for future, since I want to start coming to start taking in-person class on a more regular basis, so we will have this issue. Okay, so then I have to get back home. I'll have to catch the 6 p.m. shuttle, which is the last shuttle. So I was wondering if it is, if you're okay with starting, say, at 4:45 or so. Hmm? all 5 of you, it's okay. Huh?
So my offline class will end at 4:40.
Okay, so let's keep it at 4:50. Yeah, 4:50. So where is that class? Oh, lecture hall 6. Okay. Actually, I might go my move to lecture hall 6 also, so that you won't miss. So I'll have to wait for you, okay, to get out. So let's do that. So you get 10 minutes extra. So that's one thing. And yeah, please get, okay, the other thing is, as per the thing, I'll have to, I'm supposed, I'll be giving a quiz, okay? So we'll have to, that quiz will be, since a lot of the project work and all the assignments will give you hands-on exercises, the quiz will be a little bit on the theoretical and problem, doing problems kind of thing, and that will be like a 1-hour quiz, which so maybe a couple of weeks from now or some suitable time slot. I want to have finish a certain material. Okay, so we'll have some questions that I can assign. So that is something that we'll have to plan as well. Okay, so just a quick feedback. How have you been finding the course so far? That's a very general question. So so the only answer that you can give is not your head. So I should be asking if you're finding any issues. Okay, so in terms of either understanding, it's rushed. There's too much logic. Let me ask one at a time. So any technical issues in terms of the way Zoom is working and so on. So that that's okay. Are you finding some lectures a little bit too rushed, and that you want to go slower? I mean, you could stop, because we'll have, I think, as you move into the project, which will be very soon. While we keep discussing the project work and your progress on the project with milestones, I'll be covering some more innards of SMT solvers, etc., which will be a little bit more theoretical. I think that's when you will probably get a little bit more logic. And some of you, I know, that have had a formal exposure to logic in terms of the course. There are a couple of you that haven't. And therefore, you will have to stop and because while for the project it may not be that important, I also expect you to come out of the course understanding some of the concepts and so on, and therefore theoretical concepts also, which will be tested in your quiz and some of the assignments, and that's why I want you to make sure that you stop if some things that you don't understand. So you've seen this picture, okay? So this is kind of the architecture of an SMT solver. So as I've said, it consists of a lot of solvers. LP is one of the solvers. Reluplex can be plugged in as a solver for the thing. So they decide, they are decision procedures for certain theories, okay? And they decide the satisfiability in that theory. And usually that theory is a conjunctive fragment, okay, which means a conjunction of formulas drawn from that particular theory. There's one exception, as you saw, Reluplex is not a conjunctive theory, okay, right? Because obviously it has Relu, okay, which is non-linear from this point of view, which means that it has disjunctions and so on. But you could have these theories also be decision procedures for non-conjunctive, but usually it is conjunctive things. And then there is there is usually something called a core solver, which combines, which makes these theory solvers talk to each other. Okay, because when you have a formula like I've shown in this case, it can draw these atomic formulas from a mixture of theories. Okay, so one it could be conjunction of one. integers and bit vectors, or other things, and therefore there is combination of how these given two decision procedures which decide the satisfiability of particular theories, how to combine them. Okay, and there is quite a bit of we may cover that one algorithm as to how you combine these things. These are some of the theoretical, I would say theoretical, but they are very practical in the sense you have been using them as black boxes, okay? But there is very rich theory in developing those algorithms, and then in a way that you can show correctness and so on, okay? So, that thing is there. And then DPLLT, we went through a very quick introduction to LLT. What does that layer add, Nabin? What does DPLLT do? There was, you remember offline algorithm that I went through, and there is a question in your assignment. So in the interest of time, I'll tell you, see, these are conjunctive fragments, but you can have, as I pointed out here, it can be arbitrary Boolean combinations, okay, of these things. You can have x is equal to gy and 2x plus y less than or equal to 5, and so on, okay, or not, and negation, and so on. So there is a propositional structure. These theory solvers are able to solve things in a conjunctive fragment, like an LP solver. It is not able to do nonlinear things. So when you can combine, and that's what DPLLT does. Okay, suppose you have a SAT solver. SAT solver does not have any theories. It just has Boolean thing. Whereas here it's a Boolean combination of atomic formulas drawn from these theories. Okay, and therefore it is the reason there is a name, that there is, the reason it's called DPLLT is because DPLL is the classic algorithm that all SAT solvers use. Okay, it is named after those authors. Okay, Davis, Putnam, Loveland, and Long, I think. Okay, and I haven't gone through it yet. Okay, in the interest of putting emphasis on LP solvers, simplex and reluplex, I've kind of deferred that. Okay, I did DPLL LLT. Okay, assuming in a very quick way how you could solve Boolean satisfiability, and how that a naive version of how just a simple, what is the quick and dirty way of solving proposition formulas? You all know, no? You could draw a truth table. Okay, you can do better than that, but you could make decisions on particular variables. And let's assume it's true. Let's see if it simplifies. That's the way that you could. That is one way of doing it. Of course, that's always use lots of heuristics, etc., and that's what makes it efficient. And I have not got into that yet. Now, DPLLT, the T stands for theory, okay, because it talks to these solvers. Okay, so that's what offline did. Okay, it kind of abstracted all these things and then got into this, tried to solve it using only its propositional structure, and it takes one satisfying assignment, and then it gives checks if it is consistent with the theory semantics. That's what is the offline algorithm. And one of your questions in your thing will kind of give you an opportunity. I was going to say force you to go back and look at this offline thing. That is, yeah. So today what I'm going to do is, okay, in a way, reluplex, what it is doing is, you could do what reluplex does, okay, using a combination of DPLLT and LP solver. Okay, that is one way to do, because the nonlinearity of the relup function can be expressed as if then else, and then you can you can solve it. what ReluPlex does is it kind of pushes this DPLLT, a little bit of what DPLLT is doing, the Boolean aspect of it, into simplex, okay? And to come up with a special purpose extension, an extension to simplex, which can be considered as a special purpose thing that can do LP plus just ReLU structure, okay? Now, today, what I'm going to do is, since I have a break here, and Diganta, will be talking about Linson on Friday, and he was not able to join today. But I thought I'll take this to cover one other solver, which is the which decides which is a decision procedure. The solver implements a decision procedure. So I could be using the solver decision procedure interchangeably. Okay? For a theory called theory of equality with uninterpreted functions. That's what UEF stands for. Okay? Equality with uninterpreted functions. UF stands for uninterpreted functions. This, why? What is use of that? I'll introduce what this theory is formally. Okay? This is where I get to do a little bit of logic, and you will have to yell and scream if I'm going too fast there. Okay, so take this example. You've seen this example, right? So idea is to prove equivalence between this. I mean, this is doing it in a circuitous way through some assignments and so on. So, and we want to compare the return value of these two things. So I have expressed the return value, returned by the first function with R1, okay, and that is doing, these equalities, which denote what happens in these assignments, followed by R1, which is X times X, okay. And, here the square is computed directly, okay, and assigned Y, and we have to show this to be equal. Okay. Now you could type this thing up. This is like if you consider this a C program. Okay. You can. I mean, it's usually a 32. I mean, in C program, these things are implemented as bit vectors. Now, so you could use bit vector solver. Okay, finite bit vectors, 32 bit vectors, or you could use. In this case, you could use a linear, an LP also, correct? Okay, can you? You understand what I'm checking there, no? Okay, can I use an LP solver here? Yeah, these are conjunctions. Okay, equalities can be converted into inequalities. Okay, the only thing is there is disequality there. Okay, so the negation is there. So, but disequality also, if you could model it, except for that, you can solve it. But that is not the point that I'm trying to make here. See, you see, this is regardless of what, because both of them use a star. Okay. So you could see that doesn't matter what star denotes. In this case, star actually denotes multiplication. Okay, but these two are equal because there is here all equality is being propagated here. Okay, if you can see, this is making x1 times x1, which is the same as equal to y naught in here in this case. Okay. So and here, regardless of what star is, for all I care, star could be any function. Okay, so this whole thing is holds true no matter what star denotes. Okay, so if you were to interpret it as so, you could solve it without any interpretation for that star. That's what I mean. What does it mean? When I say there is no interpretation, it means that I don't care. It could be any function, okay? you could solve it making no assumption about what star is. And if it is true for any function, it ought to be true for star. Okay, so that is the idea. And in this case, the star is meant to be multiplication on a 32-bit vector. If you were to be, treating that star, giving an interpretation, a specific interpretation to it, then this problem becomes very, very complex in a complexity point of view, because you're multiplying 2-bit vectors, okay? And bit vector decision procedures, believe me, bit vector decision procedures in general is undecidable, whereas arithmetic is over infinite precision is decidable, okay? Which can come as a surprise to you. So what will happen is, if you were treating it as a bit operation on bit vectors, you'll have to do bit vector arithmetic, and bit vector arithmetic is modulo arithmetic, right? Okay, because there's all these wraparound and so on. So in that sense, it becomes deciding when two expressions, God forbid star, once you have multiplication, it becomes exponential, these things. Okay, these are all worst case exponential anyway, okay? But it is much harder, okay? Much more complex. You can actually try this in your Z3. You can use give an interpretation for as bit vectors. Try it. It's as a bit vector solver. It will take a lot more time than if you used this theory of uninterpreted function with equality, where it solves this satisfiability problem in that theory, which I will introduce in the next slide. Assuming that there are no interpretations for the functions. Okay. Any questions? Okay.
So you're saying where x1 star, x1, where the star was there.
Yes.
We can just replace that with a function of that.
Any function f.
As long as it just takes that one input, it's still fine.
No, f is a function. So for example, here star is being applied to x1, x1. Here star is being applied to y0, y0. So the important thing is that it could be any function f. Okay, it could be returning anything. Okay, that's what. Yeah, I mean, I guess that's what that's what you meant. Okay, but in the presence of all the rules that equality ought to satisfy. Okay, this will become clear when I show you. Okay, here is, I'm introducing you formally to what the theory is. You remember that a theory is a set of formulas, okay? And how it is these axioms, and usually these set of formulas that determine what the theory is, usually generated, freely generated. I use the term of them, which means that by instantiating one or more times all these axioms, which are like putting some constraints on the symbols. What are the symbols? There is equality, okay? And there are a bunch of functions, okay? There are a bunch of ABC are like variable. I mean, there are variables, okay? And FG, they are function symbols, okay? And they could be any function symbols. Of course, if FF, they're identical function symbol, they are considered to be the same function. But if they're, FG, F could be something, G could be something, and they could be the same function. No matter. Doesn't matter. But what they do is the equality is assumed to satisfy the rules of equality, which is symmetry, reflexivity, and transitivity. And that's exactly what this thing says. For all x, from whatever domain over which the variables range, x must be equal to x, okay? If x is equal to y, y must be equal to x, symmetry. And if x is equal to y and y is equal to z, then x must be equal to z. That's all it says, okay? And then in addition to that, that's the rules of equality, okay? And congruence is that is the only thing that is usually that I assume about functions, because that is a property of functions, okay? If they are, for any function f, okay, if the arguments are equal, then then f applied to arguments that are equal, corresponding arguments equal, produce the same value. That's what the congruence thing is saying. There are two congruence rules here because there are some predicate symbols as well as function symbols. Predicate symbols return true or false. Okay. Now, if you make true or false as some constant, you could just treat them also as function symbols. So let's assume that they are just function symbols. So any given some set of function symbols and the equality symbols and some finite set of variables, now you know how you construct these formulas. Okay. And you have to, your satisfiability should decide, your procedure has to decide if there are two things that are equal under these implicit rules. Okay. So that's what this thing. So for example, yeah, that's what I meant. Okay, we'll treat predicates as just function symbols with true or false. Okay, so when you say satisfiability, okay, for example, of course, when you say satisfiability, you say if there exists a model, you remember that the way I defined, and some instantiation for the variables in the domain in that model that makes a particular thing equal or not. Okay, so yeah. So what are some of these models? For example, T models. If your universe, that is the domain of values, just has these two elements. Okay, just a set of two elements. Okay, then is this a model? A model has a domain and some meaning you give for all these functions. Does this satisfy the axioms? For example, if I define equality, that equality symbol as this, does this satisfy? Is this a model that satisfies these axioms? Because it doesn't satisfy reflexivity. So yeah. So neither does this. This satisfies reflexivity, but nothing else. Whereas here, this is equality that satisfies all three rules. Okay. So that is what I'm saying. Now, these are models that are allowed. Okay. That meet these axioms. But now the problem that these solver for the theory of equality solves is some, yeah. I too, because I've defined equality denoting just this relation. Okay, it relates only star to star, and oh, I'm sorry. Yes. This satisfies. There is well. Yeah, I think this is fine too. Yeah, this is fine. Yes, you're right. That's a good point. Yes, because those are the only two things there. Should be okay. Yeah. So the general problem of what this UEF solver solves is, given this, where f can be any function, okay, and a is some variable there. Okay. So if f cubed of a is equal to a, and f to the 5 of a is equal to a, and FA, if you insist that FA should not be equal to A, if this conjunction is satisfiable or not. That is the kind of question that you're asking. Okay, you see, that's exactly fits into this thing. So do you think that this is true? Why?
So if f cube of A is A, so f cube of A is A, which means f raised to 6 of A is A. And so if f raised to 5 of A is A, then f of A has to be
A. F raised to the 6 of A
is equal to f cube of A. Therefore, it is A.
Yeah. Okay, that's a one way to do. So basically, what you will have to do is, if you have to check if, as a result of these two equality, under the rules, the axioms, okay, of equality and the congruence, you use the congruence thing there. Okay, so if you could derive f of a is equal to a, okay, and that is the that is the case. Okay, so for example, in here, where is that? I have it here. No. Yeah, I guess we don't need to. I mean, I'll quickly. This is the thing. I mean, I think I have a longer way of doing it. Okay, so this is what happens. Okay, f of a is equal f5 of a is equal to a, and which can be written as f2 of f3. You did a slightly different way. Okay, but the idea is the same, which means that it's equal to f2 of a. But if f2 of a is there, then congruence says if apply f to both sides, it'll be, so that'll be f3 of a, and therefore you can derive f of a. So the question is whether you can do this systematically, okay, and efficiently, okay, in even if it's not all cases, if you can do efficiently enough. How many of you have know about this union find algorithm in your algorithm course, in your graph thing? What does it solve?
How many can it looks at the edge and it only accident, like one of the nodes is not in the subgroup that we are adding.
Yeah, I mean, you're describing it in a very specific way. Actually, that can be used to compute what is called an equivalence closure, okay, of an equivalence relation. So it can actually be used, okay? And I'm going to show you that union find algorithm. One of its application is to compute what is called an equivalence, a closure of an equivalence relation. If you have a relation which equates certain things under the rules of this transitivity, symmetry, and so on, can I derive the set of all things that follow from that relation, which added to that this congruence closure, and if the congruence rule, then you get what is an equivalent called congruence closure. Okay, and you can do that, and that's what I will I will show you. Okay, so what you have is here is a simple, I mean, the algorithm. I'll illustrate the algorithm today. Okay, and then I'll discuss the actual. I don't know if I'll get time enough to discuss the how the data structure that you have seen can actually be used here. Okay. So to begin with, you have this formula. Okay. So I mean, as you could see, we had to kind of look at, analyze all possible subterms of terms that actually appear in the formula, and that's what I'm doing. So in this formula, so there is f cubed of a, starting from a, I mean a, and f cubed of a, f5 of a. So these are all the subterms of all the terms, expressions that appear in this formula. Okay, starting from a. Okay, so we don't know. So we start the slate clean. So we'll say, let's suppose that they're all in a different bucket. Okay, and then what we're computing is what is called a congruence class. It is somewhat like an equivalence class. You all heard of equivalence class, but when you add the congruence rule to it, what you get is a congruence class, and I will do the formal definition a few slides later. Okay, so let's see. For each literal, positive literal, an equality in the formula, you do the following. Merge those two classes, because f3 is equal to a. Okay, therefore you merge f3 and a. Okay, so you're keeping, this is what you're building, this equivalence class under equality. Okay, and also you add congruence thing. Okay, and then you propagate all the resulting congruences. That is, all the equalities that you get as a result of, see, merging these two classes automatically takes care of the symmetry, reflexivity, and transitivity. Of course, for transitivity to implement, if there is one common element between any two sets, these classes, you merge them as well because they'll have to be equal. Okay. So in addition to that, you have the job of propagating this congruences. So as a result of F3 being equal to A, now you can apply F to both sides. That's what is propagation of congruences. I mean, so you have yes.
So if I have F3 of A equal to A, can I now apply F3 on both sides and then get F6 is equal to F6?
Yeah. See, you don't need to look at because you have to be careful there. Okay. One of the reasons I kind of avoided doing F6, although I allowed your argument, is because if you start doing F6, F8, F9, F10, etc., where do you end? Okay. Therefore, your algorithm, all these, the reason it's decidable here is because you only are required to look at the terms that appear and subterms of those formulas. Then you look at only a finite set of things, and therefore, yeah. But your question was somewhat different. Okay, so
you said that once we merge two things, like two subterms, then we can apply congruence.
Yeah, but only I'm looking at congruence among the terms and subterms that are that exist as part of the formula. I'm restricting myself to it. Otherwise, you can this can never terminate. Yeah. So as a result of this, what happens? Okay. So when you apply this thing, F4 and FA becomes equal. Okay. So that's So as a result, this is what propagating. So derive all the equalities as a result of applying those that congruence rule. Okay, so that's what happens here. Yeah, now you could then once again propagate. You still propagate. Therefore, you get F5 and F squared. Okay.
But you already have F5 of A as A, so you can join those two.
That's right. So this F5. No. First, okay, you're doing one equality at a time. Let's do it systematically, okay? I'm only looking at this, what is green, okay? I'll get to F5 is equal to A, and then I will do the merge. You have to do systematically, and otherwise, there must be some order in which you do it, just like simplex. It does. It's very careful. It uses this variable ordering, okay? Otherwise, you could be creating loops. Okay, whenever you design these decision procedures, you have to be careful in doing it. It's good to have these rules of application, but when you actually implement it in an algorithm, there must be an order in which there might be different orders that you could follow to make it terminate. Otherwise, you can termination becomes a problem. So what it's saying is take one equality at a time that appears, then generate. I'm not even looking at all the inequalities. Inequality comes at the very end, okay? Because inequality doesn't propagate equalities anyway. So that is only to check consistency. So now I'm kind of, yeah, but like you said, there is some merging that could be done, is it? So here, no, I think that's why. This is the end of yeah. So you were, yes, so you are way ahead of me, okay? So you take this, and now you do the same thing, okay? First, immediately you do merge, okay? Therefore, you did, what I said. Now, whenever you do these merge and you create a new partial unequal class, congruence kicks in, and therefore here you could do F squared and F A are equal. Now I can do more equalities. Okay.
And then propagate once.
Yeah. So that's right. So this creates new equality as a result of merging, and therefore it creates new opportunity for congruences. And as a result of this, F3 is equal to FA. F3 becomes equal to FA, okay, and therefore F3 becomes equals, no, F squared.
Yeah, F square is equal to A in this subterm. So if you apply F on this, then F becomes equal to
FA, and therefore FA, there'll be a common thing between here and there, and therefore I can merge that as well. Okay, so now I end up having FA and A in the same equivalence class, and after that, after I've propagated all equalities and all congruences by looking at one equality in the formula at a time, I do, now I go through the negative literals, okay? And I have to see if every disequality is consistent, okay? I mean, it has to be, it cannot be, for every equality, the two terms on the two things have to be two distinct classes here. In this case, you ended up merging all of them, okay? All the terms in your thing, but sometimes you can still have some distinction. Therefore, this is unset.
Okay. So how many nodes do we have to take? In this case, we took up to F to the 5. In general, how would we know F to the 5?
Yeah, no. The restriction is only up to F to the 5. And I'm considering all subterms, okay? Ours, because F5, A was the largest term that was applicable. Actually, F square and F to the 4 is not even there. I mean, well, it is kind of there in the formula because F4 to the A and F square to the A are subformulas F5 anyway. Therefore, they're already in the formula. So you only need to consider only those things. When you propagate those congruences, you don't need to propagate congruences equality. You don't need to generate equality that have terms that don't exist in your formula. Therefore, in that sense, F to the 6A, you don't need to. Yeah. Maybe the way he looked at it, there was a quicker way to do it, but that is not. For machines, that may not be a good thing to do. Okay.
This one, in the axioms of this theory, how did we convey the fact that our functions are unintegrated?
Because I'm not assuming anything but other than the fact that it is a mathematical function.
Oh,
I did not use any rules because see. I mean, these propagation, which I'm saying, are all application of one of those axioms, the rules, which are called as the rules. And therefore, the only rule I use is the congruence rule, other than the equality rules. And I'm mixing those things. But I'm not saying O plus is associative, right? Or plus is commutative. I'm not using that. Okay. And that's why it is uninterpreted, other than the fact that it is function and the property of a function or equal arguments should yield equal thing. And that's where you limiting, okay, to uninterpreted thing. Okay, I'm going to skip this. Okay, this is just say you can also stop with that was an unsat example. This is a sat example. So in this case, propagation starts with 3 classes remaining, and x not equal to y. Yeah. So that's why it's important. This illustrates a point. Okay, you should not see. Of course, you could compute over approximation. You can merge everything. Okay, and then into one thing, but you will have to do as minimum, propagate the equality and congruences as minimally as possible, so that you keep as distinct. Don't make be over enthusiastic in merging in things, because otherwise checking inconsistencies with inequality will not be sound. Okay, so that's what it's doing. So I will introduce a few definitions and I'll stop. Okay, as to why this problem is what we did is exactly mathematically computing what is called equivalence, a closure of equivalence relations. Okay, and so binary relation is an equivalence relation if it is reflexive, symmetric, and transitive. Okay. An equivalence relation R is said to be a congruence relation. It's a special kind of equivalence relation when you have when your equivalence relation is on terms. Okay, equality over terms which have functions that have to obey this congruence rules. Okay, so yeah, so for every n-ary function, you have, if x is equal to y, that is, if it is as per the equivalence relation, then if you apply f to those equality, that's what the congruence rules say. Okay, then it's called a congruence relation. This plus all the usual rules of equivalence relation. So when you say, I mean, you know what an equivalence class is, right? It consists of all those elements in your domain. In our case, our domain is what? Set of terms. We are computing equality over set of terms. So, you know, those things which all are, you know, or every element in that class is equivalent as per these rules, and that's what is the thing. So, for example, the equivalence class under mod 3 operation. Okay, mod 3 induces an equivalence relation, right? So, what are some of the equivalence classes there? 0, 1, 2, 3, 4, 5. You know, so there are infinite number of equivalence classes. So equivalence class is called a congruence class if R is a congruence relation. Okay, so if it makes sense when you have terms, functions, and thing. So there is an equivalent thing, the equivalence closure. So when you have a relation R, which says what things have to be equal, then you can generate the set of all equivalence inferred by these rules of equality, symmetry, transitivity, and so on. Now, if you extend that relation to include all the things, that's when you're saying you're computing the closure. Okay. So, for example, if your relation that you start with says A must be equal to B, in your domain, which consists of A, B, C, and D, these things should be related, then the equivalence closure is something that you get by applying the rules of the thing and then generating all of it. But you do it, it's the smallest relation. Don't overdo it. Okay, do as, equate as many, everything that is inferred, and only those things that are, that are inferred. That's why it is the smallest equivalence relation in terms of the number of elements in this thing. But it is, when you do this, it defines an equivalence class. Okay, that will be the largest number of equivalence classes because it keeps as many things distinct. Okay. In the sense that it only includes those things that are have to be equal. Okay. Similarly, your congruence closure. Okay. You can when the congruence relation. So what the algorithm that I just showed, okay, of merging and then propagating congruences is really computing a congruence closure. Okay, of a relation, given a relation. Okay, your formulas define what terms are equal, should be equal. They constrain the terms that should be equal. Okay, and then what the congruence closure does, this is one way of doing it. You can invent another way without computing the congruence closure. Here you're computing the entire congruence closure. Okay, maybe there is some optimization that you could do, because I look at all the subterms and I did it, because here I'm computing all the congruence, the entire congruence closure, and then checking consistency with disequality. Okay. So, and that is what it does. Okay, so I still have 5 minutes. Okay, this is where I'm getting into the union find thing. This may not be, completely relevant from the point of view. If you're using SAT solvers, SMT solvers, black boxes, which is what you will be primarily doing, you can question, why do I have to get into all these things? No, but the thing is, I think, firstly, this is, university to learn things. Okay, so you should not be just limiting yourself to that thing. But there is a more important thing, because you will soon see in your project these SMT solvers and SAT solvers, even ReluPlex, etc. They may sound wonderful, but they are woefully inadequate when you really apply to real problems. Okay, and you will see, you will run into bottlenecks. Okay, very soon it will just won't come back. Okay, you put, a big enough formula, it's very easy to stump these tools. And therefore, by understanding these algorithms, what the strengths, where they don't work, where they explode, it's important that you understand some of those things, so that if you want to become an expert in using these tools, usually they provide certain knobs, and you need to know which knobs to turn which way and so on. That is when, knowing a little bit of these things will be helpful. Okay, so here is a data structure which it is it keeps track of the subterm structure. Okay, it's a directed acyclic graph among all the terms that appear in your formula. Okay, so in this formula, for example, you have f of AB is equal to A, and there is any equality. So A, B, f of AB, and f applied to f of AB, B, all possible, all these things. But this is a very compact way of representing all of them. Okay. So there are nodes, okay, and it starts with terminal nodes, which are just zero variables in this case, or zero array functions. And then this dark edge denotes, I'm sure that, yeah, I think this is okay. Just 2 minutes. Huh? Yeah, so, yeah, and then it also has a find pointer, okay? It's actually, you want to, this algorithm, the data structure, a very compact data structure, to keep the node, the subterm structure, as well as things, the equivalence class, okay, set of terms that have to belong to the same class under this equality, okay, and that's what this blue structure is preserving. So here, the term that starts at this, rooted at this, is f of AB, correct? No. F applied to f of AB and B. This is FAB. Okay. So it is saying FAB is equal to A, and therefore there is a blue arrow. Okay. And f of, in this case, I'm also saying f of, oh, that's what this thing is saying. This thing is saying f of AB is equal to A. This thing is saying f of F is equal to A, okay, is also saying. I'm not saying whether this is true or not. I'm just representing an equivalence class through these two things on the on the terms. And then, in order to make it efficient, because you have to search, okay, whenever you want to check if a particular term is, you need to keep checking when you merge things. You'll have to check if there is a common thing in the two equivalence class. Therefore, you have to see if a particular term belongs to a particular equivalence class. In order to do this, you have to do this reverse thing as well, and therefore you also keep track of all the parents, okay, of things. Okay, here you pick a one representative for the equivalence class, and that is the thing. And from that, in that node, you keep the parent, the nodes of the other terms which are rooted at that nodes that are. And the terms rooted at that will be equal, will be the same class as this representative class. Therefore, that searching will be important. And then And yeah, union fine. Okay, this is fine. Union is merging. Okay, you have this kind of a data structure using union and merge, and then a little bit of extension to congruence. You can very efficiently implement that algorithm that I've done. So I will do that next on Friday. And Friday, Diganta will also complete discussion of LinSim, so that then you now have all three tools that you need to do. So starting from next week, we will be defining, the project, okay, and then give some warm-up exercises for you to get warmed up into using these tools. Yeah. Okay. Yeah. Since it's late, you reserve your questions to next class. Okay. Very nice meeting you, and hopefully I'll continue to. Yeah, I will. Okay, not hopefully. Okay. Okay. Yeah, you can. Yes. No, Thursday will be an online lecture. No, but I will come here. Friday, I'll come here physically. Yeah. The Thursday, that is tomorrow, for the thing, I will not be coming in. What happened to my... Oh, stop sharing. Why am I not getting this? If I have to end that, I have to end it properly. Otherwise, it'll not. Even then, I'm not getting that. No, it's here. It's already. Okay. Stop.
I think we just end.
No. I have to stop share, no? Okay. Oh.